Then how was it getting recorded earlier? Anyway, now I've started. Okay, so a handle of a right sentential form is a substring beta, which is the right hand side of a production. So if I have a production A produces beta, then beta could be the handle of a right sentential form. That is condition number 1. Condition number 2 is reduction of beta by to A. You are doing the reduction. That is, you are doing the rightmost derivation in reverse order. So in production, you replace the left-hand side non-terminal by the right-hand side string. In reduction, you replace the right-hand side string by the left-hand side non-terminal. So you're saying that the reduction of beta to A is a step along the reverse of a rightmost derivation. So it brings you to the previous right sentential form. If these conditions satisfy, then beta is said to be the handle of that right sentential form. So let us look at it in a little bit more symbolic terms. The next point is the same thing stated in specific symbolic terms. So let's say S rightmost derives gamma AW. What is gamma? Gamma is a string of any terminal, non-terminal. Naturally, A is a non-terminal and W is a string of terminals only. It is a right sentential form. So this tells me that A is the rightmost non-terminal, because to the right of it, W is a string of terminals only. So A is the rightmost non-terminal, which means in the next step of derivation, A has to get replaced by beta. For the using the production, A produces beta. So the next step is gamma beta W, where beta is a sequence of tokens or terminals. If this is the case, then the substring beta in this sentential form gamma beta W and the production A produces beta is the handle. So if I have to do a reverse of the rightmost derivation, that is, I have to come from gamma beta W back to gamma AW, then in this right sentential form gamma beta W, I need to know the substring beta, which was last generated, and I need to know the production A produces beta, so that I can substitute this substring by A in the reduction and go to the previous step. So this pair of the substring and the production makes the handle. So this is again what we have seen, but we are just taking a relook. So this is the column of sentential forms in reverse order. So if you read it from bottom to top, it is the forward normal derivation, rightmost derivation, and this is a sequence of productions. So what happens is, if you consider the first sentential form ID star ID plus ID dollar, then in this sentential form, what is the handle? The handle is this string ID along with the production F producing ID. Why? Because if you look at the previous right sentential form, F star ID plus ID, in that F was the rightmost non-terminal, and you could replace it by ID, F producing ID, this production, to get to the next one. Now, if you have this sentential form F star ID plus ID, then what is the handle? The handle is F. Because how did you get that? You got it from the previous one by replacing T with F in the production. So the handle of F star ID plus ID is the string F with the production T producing F. So this is the sequence of handles that you can see. For example, take any other. Let's say what is the handle in this? T star F plus ID. In this, the handle is T star F, the string T star F, with the production T produces T star F. Right? Because if I replace T star F by the left hand side T, if I do this reduction, I go to the previous sentential form, which is T plus I. Right? So we can say in a very simple terms, if I have to do this parsing, if I have to construct this rightmost derivation in reverse order, that step that I need to do repeatedly is in the sentential form. I need to identify the handle and replace it by the left hand side of the corresponding production. And this process is called handle pruning. This process is called handle pruning. So handle pruning starts with the sentence, identifies the handle, does the reduction, gets to the previous sentential form, again identifies the handle, does the reduction, again goes to the previous sentential form, identifies the handle, does the reduction, keeps on doing that till it reaches the start non-terminal. So that simply is the parsing process. Now, a very significant observation that we can make is the fact that wherever I get the handle, we have seen this here when S produces gamma AW, that produces gamma beta W. What we have seen is obviously whenever I get the handle, to the right of the handle, I will always have a terminal symbol, and every symbol to the right of that are terminal symbols. This is guaranteed by the rightmost derivation convention. Right? So this gives us a way to actually process this in the PDA by wherever you have the handle. Say if I take T star F plus ID, then up to the handle from the left is the part of the sentential form which will reside in the stack of the PDA. Whereas anything that is from the right of the handle to the end will be in the input. And the symbol which is immediately to the right of the handle is indeed the look ahead. Is indeed the look ahead. That is the first symbol in the input. So that is the look ahead. So this is the basic structure that we are going to follow in the LR parsing. So LR parsing is nothing but a handle pruning mechanism. The question obviously is, how do we build the state machine so that at every stage we can know whether we have found a handle or we need to input or need to take more inputs from the input buffer to build the handle. And once the handle is at the top of the stack, it will always be on the top of the stack. Then we do the pruning and again proceed to find the next handle. So that is the basic process that we do. So this is our LR parser. We have mentioned it earlier: input buffer, stack of symbols, and these four actions: shift, reduce, accept, reject. So this is the point that we are adding now. We are saying that a parser operates by shifting tokens onto the stack. If I shift the token from the input to the stack, then what I'm trying to do is to look for handle in future. Handle is still not found. As soon as when a handle beta is on the top of the stack, the parser will reduce beta to the left-hand side of the production. That is the reduction process. So stacking in this way, I will eventually find the handle at the top of the stack. This is guaranteed by theory. We are not proving that, but this is, we are just seen that by observation. If you go back and see it here, you will always see that it is always on the top of the stack that it will occur. You can refer back to the example we did. So when a handle beta is on the top of the stack, parser reduces beta to the left-hand side of the production. And parsing continues until an error is detected or input is reduced to start symbol. Very simple mechanism. Shifting onto the stack, continue till you find beta or a handle on the top of the stack and reduce it by the handle, by the corresponding production, and take out the right hand side of the production, that is beta, and push in the left hand side of the production, which is non-terminal A, as we have said. And then you continue doing this till you either encounter an error or you reach the start symbol. So what all we need to do is to create a state machine, create this parse table, so that this process can be controlled in the manner in which the grammar dictates. Right? So that's what we are going to do. So we'll start with the simplest of parsers, which are called LR0 parser. We need these two definitions. These we have already talked about. So I'll skip. The first of a string of terminals and non-terminals is a collection of all terminal symbols or epsilon that could be derived from this string alpha. That is called first. And follow is defined for a non-terminal. Follow of a non-terminal is a set of those terminal symbols or dollar which could occur immediately to the right of that non-terminal in any sentential form. So these are the two definitions. We will keep these in little bands. We'll see that in the process of our design, we'll need these two definitions to be used. Okay. Now for the parser construction, I introduce another concept, another definition. We are first going to talk about LR0 grammars. So what is an LR0 parser? We are saying 0. In LRK, we are saying K is equal to 0, which means that it has no look ahead. That means that grammar can be parsed by looking at the stack only. I do not need to look at the input. I look at the input, I shift. It is not that I look at the input to decide whether I have a handle. That decision happens only on the stack. The grammars for which this can happen are called LR0 grammars. We will see examples soon. So we can make the shift or reduce decision without any look ahead token, not looking into the input. So this is based on an item or a configuration. So what is an item? The item, just note this very carefully. We will use this very consistently. Suppose I have a production A producing x1 to xn, where any xi is either a terminal or a non-terminal. So I have a production A produces x1 to xn. In that, somewhere between xi and xi plus 1, I put a dot. Dot is like a marker. I put a marker dot. Now this can appear anywhere on the right hand side, which means that it could be before x1, it could be anywhere in between, or it could be after xn. So in any of these n plus 1 positions, a dot can happen. And depending on the position of the dot, for one production, we will have n plus 1 different items. Now, the dot symbol may appear anywhere on the right hand side. What does it denote? It says that how much of this production I have actually seen so far. And I'm doing a left to right scan. So things are happening from x1, x2, and so on in the right hand side of the production. Now the dot, if I have a dot after xi and before xi plus 1, then what it means is that I have seen up to x1 to xi of this production that has been used. So that is the part that appear on the top of the stack. So I'm moving the dot, scanning what I get to see, and I keep on moving on to the stack. That is the shift operation. And xi plus 1 to xn is what I have not seen. I expect to see. I do not still know the input. So I would expect to see it. So there could be at any point, depending on how far I have seen, there could be multiple expectations. And depending on what I get in the input, one or more of these expectations will tend to be satisfied. And that is what we are primarily looking at. So just to, this is the meaning of the item. We will see it more clearly in a couple of slides. But just the core take back is an item, LR0 item is a dot marker on the right hand side of a production at any point. So that it means that to the left of the dot is what I have already seen and is on the top of the stack. And to the right of the dot is what I expect to see at a certain future point. So an LR0 state, then we'll say that an LR0 state is a collection of a set of LR0 items. A LR0 state is a collection of a set of LR0 items. Right? So these are the two definitions, items and state. Let's look through examples. Examples are easiest to understand. Okay. Now let us consider a grammar on the left. S produces X. Immediately you don't have to really worry a lot about what this grammar means. But of course, you will be able to figure out that this is some kind of a parenthesis expression that is being done with comma separator as well. So S produces X. S produces within parenthesis L. L produces S back. L produces L comma S. This is the grammar. Whatever. Obviously, clearly this is a context-free grammar. Now, given this, for the parser construction, what we do first is we augment this grammar. What is augmentation? Augmentation is we introduce a new start symbol and add a production where from the new start symbol S primed, we are producing the earlier start symbol S. Why are we doing this? Very simple. We said if I go back 2 slides, 3 slides, 4 slides here, not here, even earlier. We said in handle pruning that my basic parsing step or construction of the rightmost derivation in reverse order is identify the handle, reduce, identify the handle, reduce. And for identifying the handle, keep on doing shift. And when do you stop? When you get the start symbol. Now the question is that the start symbol itself would be on the right hand side. So I may come to the start symbol, but I have not actually finished the reduction process. I have not actually finished the derivation process. So what we want to do is to make sure, doing a simple trick to make sure that we have a unique way to know that the derivation has ended. So if I put an additional start symbol S prime and an additional production, single production like S prime produces S, and then I start my derivation process from S prime, stay convinced that the language does not change, right? Because all that you have is one additional step in the derivation. But then everything is produced from S as in G6 here. But in terms of the reductions in reverse order, in terms of the rightmost derivation in reverse order, I'm doing reduction, doing reduction, doing reduction. So what will be the last reduction that has to happen in this augmented grammar? Is obviously the first production that happens in the augmented grammar. And that production is always this S prime produces S, this auxiliary additional production rule, which will happen only once, happen only at the beginning, and must happen for any sentence to get generated. So that gives us a very easy way to say that if I have a reduction by rule 0, then I have a success. If I have a reduction by rule 0, then I have a success. So that's a simple trick which allow me not to look for anything else as a terminating success condition. So that is the augmentation, auxiliary augmented grammar form. Then these are the couple of definitions. You have to really start understanding them. LR0 item we have introduced. LR0 item is a production in G with a dot at some position on the right side of the production. So we can say that if I look at the production 2, S produces this opening parenthesis, L closing parenthesis, then dot could be at the beginning. This is one item. Dot could be after the opening parenthesis. So this is another item. Dot could be after the L. This is a third item. Dot could be at the end. This is a fourth item. There are 3 symbols on the right hand side. So there could be 4 possible items. So these are the possible items from production 2. Similarly, every other production will have a number of items. So 1 will have 2 items. This will have 4. 3 will have 2 items. And 4 will also have 4 items. Now we're saying something interesting. We say that we have, for an item, we have a concept of a closure. What is a closure? Closure is add all items arising from the productions from the non-terminal after the period in an item. Now what can happen? I'm putting a dot on the right hand side. Okay. So that dot could be before a terminal or it could be before a non-terminal. Now, what does that dot indicate? Remember, recollect. We are saying what do I indicate? Is anything which is before the dot has already been seen and in the top of the stack. And to the right, x1, xi plus 1 to xn is what I expect to see. Now in that, if xi plus 1, the symbol immediately to the right of the dot is a terminal, then I surely know what I expect to see. Because it's a terminal. So I must be able to see that terminal to be able to proceed with this production any further. Clear. So if it is before a terminal, if the dot is before a terminal, then there is only one item that I am concerned about, only one way to proceed. But consider this other item where the dot is before an L. So dot is before a non-terminal. So this is xi plus 1 is a non-terminal. Now what do I expect to see? I will expect to see anything that this L can produce. What I expect to see are several possibilities now, not just one terminal symbol. And those possibilities are all that L can produce. So what can L produce? What can I expect to see from L? Is I have to take every production from L and consider that there is a dot on the beginning of the right hand side, wherein it means that I have not yet seen anything in this production, but I expect to see whatever follows that dot. So I do that. This was the original item S produces opening parenthesis dot L closing parenthesis. This is being a non-terminal. I consider both the productions from L and put the dot items that have dot at the beginning, because if I have a dot before L in this first item, then I expect to see anything that happens from L, which could be by the production 3, which is L produces dot S, that item, that is, I've not yet seen anything in this production, but I expect to see anything that happens from S. Or it could be by the 4th production, where L produces dot L comma S, that is, again, I have not seen anything and I expect to see anything that happens from L. So that is the basic process of closure, that whenever the dot precedes a non-terminal, you include all the productions of that from that non-terminal and put the dot at the beginning on the right hand side to include those items. So here again we have got 2 items. Again in L produces dot S, This goes transitively. It does not end right here in one step. Here we are saying that in S, L goes to dot S in this item. What do I expect to see? I expect to see something that happens from S. So I will have to also consider the productions from S. So S produces X. So L producing dot S also generates item S produces dot X because dot is immediately preceding S. Similarly, for production 2, I have S produces dot, opening parenthesis, L closing parenthesis, because dot is preceding S. So 2 more items get included. From the item that we got from production rule 4, L produces dot LS, I need to have a closure with L, which I have already taken. So no more items get added. So this says that the closure of the item S produces opening parenthesis dot L closing parenthesis are these items. So you see, I mean, this is a very organized way to explore possibilities. Since I know that the dot is before a non-terminal, I am expecting to see something. I'm expecting to see whatever can come from that non-terminal. And that in turn could lead to something that comes from other non-terminals that this non-terminal generates at the beginning, then and so on and so forth. So closure basically gives me all the possibilities. So with all these possibilities, I know that, well, I would eventually know that I can get an X to continue, I can get an opening parenthesis to continue and so on. So that is the closure. So whenever we have an item, we will always have the closure of that, which means that if the dot of that item is before a terminal symbol, then we do nothing. But if it is before a non-terminal symbol, then we include all the items that are generated from the productions from that non-terminal with the dot being at the beginning of the right-hand side. And we continue this process transitively till we end. And we are guaranteed to end because the number of items as such is finite. So any item that is included in the closure is certainly one of the valid items. Okay. So we will see how, I'm just trying to give you the concept of this item. And so it is a very organized exploration mechanism. If you recall, I mentioned that an LR parsing is beautiful because it is linear. It's beautiful because it does not go back and forth. It's beautiful because it does not backtrack. So since it does not backtrack, what it tries to do, and that's what we are constructing here, is a very organized, structured way to keep on exploring as to what to expect, and then confirm from the input as to out of those what has actually happened. That part is taken care of. We keep on doing that. And if the string is valid, I'm guaranteed by the theory that I will eventually find a handle which was used, whose production was used to come to this right sentential form. So I can reduce by that handle and go back to the previous sentential form, and the handle cloning happens. So that's the whole thing we are trying to structure it. The third that I mentioned is state. A state is a collection of items. So if I have a set of items, then it can represent a state. We will see what is the concept of state. How does whatever we are saying is a collection of items is called a state, is eventually what will become the state of the DFA. So we'll see that these are actually representative of the states of DFA, the finite automaton which will drive the PDA. But in terms of what they are identified with, is a collection of one or more items that the state represents. And finally, what are the actions? These are 4 possible actions and the go-to. So actions, again, we have through the example talked about this, but let me talk about this in the context of the item. That is, I have a shift followed by a number, which means shift on input symbol to state number. So we had something like S5. So shift the input symbol ID onto the stack and go to state 5. When will that happen? When the dot precedes the terminal symbol. If the dot precedes the terminal symbol, I know that I'm expecting to see that symbol. And I can only proceed if I see that symbol. Anything else is not possible. It's not possible according to the production. So if the dot precedes a terminal symbol, then I know there's a shift. It has to happen. On that symbol, I'll shift to a new item. I would say that in this production, I've gone one step more. What is reduction? Reduction is beautiful. Reduction, when will reduction happen? When I have seen the entire of the right-hand side. When I'm still expecting to see some part of the production, yet to generate something naturally, I could not have come to a sentential form where the right-hand side have been expanded. I can expect that a reduction can happen. That is, I can go back to the previous sentential form only when I've seen the entire of the right-hand side. So the reduction will happen when the dot in an item is at the end. Unless I have an item where the dot is at the end, there is no question of having a reduction. Right? And then we will put a reduction by the corresponding production number of the handle on all input symbols. Remember, we are doing LR0 construction, which means that we are not doing any look ahead. So if a state has an item where the dot is at the end, then no matter what is there in the input, I don't look at the input. In that state, I reduce by that item. But by that handle, by that production. So I put that production number. This is my rule number 2. Rule number 3 is accept on reduction by the augmented production S prime producing S. This I have already discussed at length. Why we have augmented, and certainly whenever I get to, I'm about to do a reduction by S prime producing S, then I'm certainly accepting the string. Reject is anywhere that none of the 3 above have happened. There's no shift, there's no reduce, no accept. In all state and input configuration where none of the above 3 have happened is a reject, or error conditions that cannot happen. And finally, the go-to is on transition of non-terminal after the reduction has happened, because I've gone one step back. I once got one step back in the sequence of rightmost derivation. So now, as I have gone one step back, I have to see how did I come to this step. Naturally, the dot must have been before the non-terminal on the left-hand side in that production, so that I could expand and get the entire right-hand side in my next step. Okay? So it has to be done by that process. We'll see that details. So this is the outline of the LR0 parser construction process. Let me, I'm feeling like getting back for questions, but let me just do 2 simple examples, and the questions will be more meaningful. So let us consider a grammar, pathologically simple grammar. S produces A. One production. One non-terminal, one terminal, one production. Nothing can be simpler than this. So what do? I augment the grammar. S prime produces S, so that I can find the accept. S produces A remains as it is. The language of this grammar is simple. It can produce only one string, that is A. Now what I do is I start with the first production, the augmented production, and put the dot on the right-hand side, beginning of the right-hand side. Why? Because I'm starting the process. I have not seen anything. Obviously, I have to start from S prime, that is given, augmentation. And I haven't seen anything, so on the right-hand side, the dot has to come at the beginning, because to the left of it, there is nothing. The stack is empty, everything is empty. And then that S Now, the moment I have that, so that is what I have here. S prime goes to dot S, this item. But the moment I have that, S is a non-terminal. So I'll have a closure for S, which brings us an item from S produces A. Intuitive justification is having the dot before S in the production S prime goes to S is saying that I haven't seen anything yet and I expect to see whatever happens from S. And what happens from S? That is, an A can happen from S. So now I have an A can happen from S. So I put a dot here. There is no more closure to do. So I put all this together into one set and I call that a state 0. So state 0 or the starting state of the DFA is always a state that contains this item. S prime produces dot S. Now I say that, okay, now I will have transitions. Now I say that, okay, what was my rule? If the dot precedes a terminal, then I know that I expect to see that terminal. So I will do a shift. Because if that terminal is seen in the input, I know, okay, this is where I am and I'm making a right program. Now, what does that shift mean in terms of the item? It will mean that I was expecting to see an A and now I have seen the A, so the dot has to slip over this symbol A. So the dot slips over one step because I've seen an A and I get to this item. I put it in the table that on state 0, when I see an A, I do a shift and I shift to a new state, which I'm calling state. Now, once I get an item, what is that I have to do? I have to compute the closure. Here, there is nothing to compute in terms of closure because this is already a completed item. What are the other possibilities from state 0? I say dot is before S. So what does that mean? That means that I'm yet expecting to see anything that happens from S. So what can happen from S? What can happen from S are all possible production and get reduced to S in eventual time. So from this, if I have seen everything from S, then I expect to slip over this dot over S and get to a new item here, which is my go-to transition. So if things have got all reduced to S, then I have actually seen whatever S could produce, and I must go to the configuration where the dot slips over S because I have seen what S can produce. So on state 0, in symbol S, the non-terminal symbol S, I go to this item. Again, for this item, I need to do a closure. There is nothing to do closure for because there is no dot preceding a non-terminal. So the closure is itself, I call it state 1. And that is what I write down here. I say in state 0, if the symbol is S, that is if I have just reduced to S. What is the meaning of the symbol being S? S does not occur in the input. This part is what occurs in the input, A and $. S does not occur in the input. What is the meaning of slipping over this? Is I have seen whatever has happened from S. How is that I could have seen whatever happened from S? When things have got reduced to S. So if I have done a reduction to S, then if after that reduction, if my state was 0, then my next state should be 1. What happens in state 2? In state 2, I have a complete item. This is called a complete item. If the dot is at the end, we typically refer to it as a complete item. So obviously, if it is a complete item, then I have seen it all. So which means that I have got a handle. And that handle is the handle is A, and it is for S producing A. Okay? So in this state, I can simply reduce by S producing A. In state 2, I say this is rule number 1. The augmented one is typically marked as rule number 0. This is rule number 1. So I say in state 2, I just reduce by 1. So I do not care about what the input is. Whether it is A or dollar, I don't care. I will reduce by 2 because I haven't got it. Finally, what happens in state 1? In state 1, I also have a completed item. And that item is from the production rule 0. And it has got a completed item, which is the handle for the production rule 0, which is the augmented production. So this means that when the dot has come to the end of this production, it means I have seen to the left of it is S, which means anything that X could generate, my original grammar could generate, I have seen. So this means that I'm done. I'm successful. So I put that as accept. Actually, I should put accept in this case also, because I'm not looking into the input, but I've just for the conceptual clarity, I put the accept below dollar, because at this point, obviously, I'll just have dollar. So this is my LR0 parser construction. Let me do one more example and then take questions. Remember this grammar is S producing A. I've just augmented this grammar a little bit with a right recursion. And so S produces AS or terminal string BC. So there are two productions. S produces AS, S produces BC. I augment with an auxiliary production. And also I put down what is the grammar, or what is the language, which is very simple, because I can, then this is S occurs only here. So I can have one or more recurrences of S. So that I'm sorry, 0 or more recurrences of S. So which tells me that I can have arbitrary number of A's, which is A star, and then S produces BC. So that's how it ends. This is the language. Okay. Naturally, the starting item S produces dot S, state 0. What do I need to do is to do a closure, which means S has a dot before it. So I will include both the productions from S and put a dot at the beginning. I put that. Now, in the two added items, the dot is before the terminal symbol. So there's nothing for the closure. So this is my state. Now, what are the possibilities? The dot is before A. So I expect to see an A. So I'll have a shift transition on A, wherein the dot moves over this A. So I get from S produces dot AS, I get S produces A dot S. And the moment I have A dot S, I need a closure of this S. So the other two items get added. Very simple. Or I could have on this state 0, I could have, I'm expecting B. So if I see B, I will shift that. So on B, I shift. My dot moves after B because now it is S produces B dot C because I've seen B. I'm expecting to see a C. And now the dot is before a terminal, so there is no closure. So with this, what I get is in state 0, I have on A, I go to state 2. On B, I go to state 3. Certainly the other one is simple. If I have already seen anything that S produces, if it has been reduced to S, then I have a transition on S, which takes me to state 1, which is the go-to function at the end. Now, what happens in state 2? In state 2, again, I can have transitions on A and B because the dot is happening before A as well as. So if I have an E in the input again, then the dot moves over, it becomes A dot S, which is this item. And the same set of closures. So I can see that if I have an E again, then I actually get back to this state because I have the same set of LR0 items. So this is, I can see that this is the possibility of having one A, and this is the kind of the loop, which keeps on giving you 2A's, 3A's, 4A's, like that. It keep on continuing. And going over through B is the case where you have 0A. So this is a transition on A. There could be a transition on B. This dot moves over this B, and that will produce S produces B dot C, which is same as the item in state 3 and has no closure, no more item to add for closure. So on B, it comes to state 3. You can see that you can. So here you can come as B, you can come A, B, you can come A, B, you can come A, B. It keep on happening there. There's a dot before S. So when I have reduced to S, I've seen everything that S can produce. The dot slips over this, and I get to this item. S produces A dot S, which is a completed item and has no closure. So this is my state 5. So if I look into state 2 now, I have on A, I shift to B, shift to state 2 itself. I stay in that. On B, I shift to state 3. And on S, if there's been a reduction to S, then I go to is state 5. On 2, on S, I go to 5. That is, if I've been reduced to S, while before that I have been in state 2, then I go to state 5. Let us come to state 3. In state 3, I can have only one transition, which is a shift, because I'm expecting a C and I can only move if there's a C. So if I take that move, then I go to S produces BC dot. The dot moves to the end. So on state 3, on C, I have a transition to state 4, S4. What happens in state 4? I have one completed item, S dot BC, S goes to BC dot. So if I'm in state 4, I don't care what is there in the input, I just reduce by this production, which is S produces BC, because I've got the handle. So it is R2 all through. Similarly, in state 5, S produces AS dot, I've got a handle, it's the completed production. So I reduce no matter what is there in the input by production 1, that is S produces AS. And finally, in state 1, the same thing as having reached the end. So I accept. Again, I could have shown accept in these as well, which are pathological, but certainly when I come to accept, naturally it has to be on the input there must be $, and I got the accept. So if you follow the state machine, and if you keep on doing this reductions, you will be able to parse any of these A star BC strings. And mind you, in both of these examples, we have not required to look into the input to decide if we have got a handle, if we have got a situation for a reduction, because whenever a completed item has happened, which means that I have already got the handle, that item was alone in that state. So just by knowing that I'm in this state, I know that I have a completed item to reduce. So this is I will not step through this, because we have done that for a more complicated example already. But this is just to show that for this particular grammar and the table that we have formed, this is for AAABC string. How does really the shift happen? So you can see that it is shift very clearly, because the first reduction can happen, because it's a right recursion. So this is a right oriented tree. So which means that the first reduction will happen, that of BC coming to S, and then the others, and that is exactly what happens here. I would request you to work this out at home by hand, not looking into the workout, and then just verify that you are doing it correctly. Okay, so at this point, let me stop and get back to take questions. Yes, Shomni.
Sir, can you please explain the reduce part a bit once again? Uh, it was little unclear. I mean, how the reduce is exactly, when exactly to reduce.
See, at any point, if you just say, go back here, the reduce is basically coming from this. So at any point, when you have got the right hand side of the production, you have seen that. So that is the point where you would have to reduce. So what does that mean? That will mean that in terms of item, when would you be able to decide that you have seen the whole of the right hand side? When the dot has moved to the end? What you are doing, what is this item business doing here? What is this item business doing here? It is telling you how much you have seen and what you expect to see. So when you start at this point, just think about this simple construction that tells you all. You start with this, you see that this is your starting point. So you have seen nothing and you expect to see whatever S can be. So you explore in a very structured way what can S give you. S can give you these two. And in the if S is giving you this, then A is expected in the input. If it is giving you B, a B is expected in the input. So you say that, let me see, has it given me A? If it has given me A, then I will go to this item which tells me that I have already seen an A. And what do I expect to see? Whatever S can give me. That's the simple meaning of the item. On the other hand, if it gives you a B, then you say, okay, I'm going to this item, so I've seen a B. Now I expect to see a C. So what are these transitions meaning? Is this shift that I've got an A, so I take that A and consume that. And now I expect to see an S, and that in turn tells me that I expect to either see an A or see a B. Now I've seen a B. What do I expect to see? I expect to see a C, nothing else. If I've seen a B and I get an A in the input, it's an error. I seen a B, I get $1 in the input, it's an error. I seen a B, if I get a B in the input, it's an error. I've seen a B and I expect to see a C, exactly. So if my input is C, I'm in state 3, if my input is C, then I come to S produces B C dot. So what does this tell me now? This is the point of reduction. What does this tell me now? This tells me that I have already seen BC. So that is the handle. I've just seen the BC. That's the handle in mind. So I've seen the BC here. Look at the point below. So this is the handle in this production, in this sentential form, and I have to go back one step and replace it to S. So that is the reduction process. So the fact that I got a completed item tells me that I have to reduce. Tells me that I have to reduce. Now it's a different matter that here I'm just deciding based on the fact that I'm in this state and have a completed item. We'll see the complications of that. Forget all those right now. But I have a completed item which says that I've seen all of this right hand side just now, and I don't expect to see anything else immediately. There's something. There'll be lot of more things. There may be a lot of more things in the input, but that's not my point. What I've got is I've just completed the right hand side of a production, so I have got a handle. So I will reduce by this, and that is the action reduce that we are putting in here. I've done
in this example.
Okay. Just let me finish. I have done that, right? So as I have done, then what happens? Where did you come from? Where did this come from? This came from you have got two possibilities. For example, in the third derivation, if you see, where did you come from in this BC? It came from state 2. So when you reduce by removing this BC from the part that you have already seen. So removing this BC. So you are back to state 2 now because you have done this reduction. So when you have put this S, before putting this S, you must have been in state 2. Think about it. You have an A, you are in state 0. You have an A, go to state 2. You have another A, you remain in state 2. You get a B, you come to state 3. You get a C, you come to state 4. Here you have got this reduction, got this handle BC. So you're removing that with S. So as you remove this, you step back to see which state did you start getting this handle. You started getting this handle in state 2 because you got this BC after that, the 2 symbols. So you back up 2 symbols and see where had you been after you had seen AA and was expecting to expand on S. So you go back to state 2. And in state 2, now what you have got? You have seen whatever this S could produce because you have already done the reduction. You have done that part of S produces BC. So now in state 2, what you expect in terms of the S is to see a completed item. So in state 2, on this reduction, now you say that my state is 5 because I have an S coming here. So I make a transition on state 2 to state 5 and I get another completed item, which is what I have got as a handle as AS here. I've already got the handle, the right hand side of the production. S produces AS. So I reduce by that. As I reduce by that, I have to see where did I come from. I came from AS. Right? So I had A from state 0, then S from state 2. So AS is what brought me here. So after this A, when this A happened, I was in state 0. Right? So you calculate as to whether you came from the state 2 to here, because you can come here as AS or you can come here as AS. So in the first case, you will back up to state 2 and will again come to state 5 to do the next reduction. And in the second case, you will back up to state 0 and do a reduction, which is basically accept. So that's the basic reduction process. Does that clarify?
Yes, sir. Yes.
I understand, but
Yes.
you have to do a little bit of hand weaving, little bit of some simple. I mean, there are a number of grammars I've given as practice. Just do a little bit, and slowly you'll start understanding. But the important thing shift is easy to understand. I'm sure shift most of you didn't have any problem. The second is identifying the handle. That is when I've got a completed item. I certainly have an handle. So that is the second part, which is less obvious. But once I have the handle, then naturally I can do a reduction. The third part is a tricky one, is to back up. Is if I've got the handle, I'm doing a reduction. So that means in this state machine, I have been traversing paths. So I have to back up on that path. And that is the reason you have the stack. What is the stack doing? Stack is every time you take a step, the stack is pushing those symbols. So stack has a full trace of the fact that what are the states that you have gone through. So it can back up as much of what you have now. We are now reducing. The handle that you are now reducing is what is taken care of. So when you have BC as a handle, you back up to state 2. And then you know that you are exploring on S. So you go to state 5. And when you see another completed item, okay, AS, you have got another handle, which is the right-hand side here. You'll go back to S. Then you have to see after this first A, which state you are in. So you have to go back one S and one A. In this case, that going back is to state 2 itself. So after the first A, you are actually in state 2. This is not a confusion because all these will be on the stack. So you just take out 2 symbols. Your handle has a length 2, so you just take out 2 symbols from the path. So state 5 goes out, state 2 goes out, another state 2 exposed. And on that state 2, now you have seen this S. This is the first sentential form. Now you have seen this S. So you again make a transition to 5. You get this completed item. So you have to reduce AS to S, and in the process back up again 2 steps, which is 5 back here, but now not back to 2, because the first one you get from 0, and that's what your stack will say. So you go back to 5, then go back to 0. So you are back to state 0, where you have got this S. This is the S, the beginning S that you're exploring. So in state 0, when you get S, you go to state 1, and that's why you exit. So that's the plain simple process of how things work in terms of this. Let me. Yeah. So in LR0, Ishan, I'm responding to Ishan. In LR0 there is no look ahead. So just based on the state, I know what do I need to do. If I have a state where reduction has to happen, then no matter what the input is, I just don't look at it. The state tells me that I have to reduce. So which clearly tells me that reduction states will have only one item, completed item, in an LR0 grammar parser. We will see how this will immediately break. But first, let me get if you have any questions. Anyone else? Any other question?
Nothing else, it seems.
Okay. So let me go back and proceed. Okay. So we have done.
Sir,
Yes.
so how do this handle, not in this case exactly, but supposedly for S, there were 2 options. It could read forward also. Also, it is possible that it might reach S prime. So in that case, how will this handle?
See. Let us not complicate life. In this example, that did not happen, right?
Yes, yes.
Right. So let us take one step at a time. So the next step will be to stumble. So I'm saying repeatedly that I could do LR0 because every time I got a completed item, that was the only item in the state. So with that, we could do one pathological grammar, which was this, which has only one sentence in the language, and we could do another, which is kind of an infinite language, but a very simple language. I will just do a small tweak on this grammar. The same grammar as before. S produces AS, but in place of BC, I'm just using A. I'm actually making it simpler in terms of the grammar and the language, but see the disaster that it will lead to. So augmentation, the language is simple. It is any number of 1 or more A's in the language. Keep on doing state 0, very simple. S prime produces dot S, dot AS by closure, dot S produces dot A by closure. In both of these, I expect to see an A. So I see an A, and I go to state 2, which is on state 0. On A, I go to state 2. So I have A dot S coming here, and I have a closure, which is dot AS, and S goes to dot A. These 2 items, item in the serial 2 and 3 here, are coming from the closure of it. And also I have done a shift here on S goes to dot A. So this dot will slip over here as well because I do not know which of these are happening. So I have a dot at the end. So this is the state 2 I got. In state 2, I have naturally, I expect to see A in item 2 and item 3. So there is a transition on A, which brings it back to Excel. I have a dot before S, so I have a transition to state 3, which is a completed item. S produces AS dot. In state 0, I have transition to. So that's something. Now, if I look at state 0, it's very simple. I have a shift on A to state 2, and I have a go to on S to state 1. State 1 is accept state. State 3 is simple. I have only one completed item, which is by the rule number 1. So I have R1 on both inputs. Look at state 2. On S, it has a go to on 3, which is fine. Now, what is happening here in terms of the blue and the red? If I consider here, what should I do? I have a dot before A, which means that I'm expecting to see an A. I'm expecting to see an A, which means that I must shift. That has been the protocol. And go to state 2. So I must, on A, I must shift on state 2 and go to state 2 again. But the other one says that I have a complete item. See, till this point, the complete items always occurred in isolation in a state. Here it does not. It occurs with other items. And with this shift item, I have a complete item which says I have just seen an A, which means I've got a handle. So on that handle, I should reduce. Now the question is, which one should I do? So on A, if I have an A, if I take this reduce, then according to our convention, LR0 convention, both of these entries should be R2, reduced by S producing A, because I have a complete item in that state. But if I take, when I look into the fact that dot is before a terminal, so that gives me a shift mandate, which says that on A, I must actually shift. So I can see that on input A, I have a decision to make between whether to shift or to reduce. So if I just blindly reduce without considering the input, then I may actually get wrong, because what will happen is I got an A and I will reduce, I will get back here to state 0. So I will not be able to parse AA. I will not be able to parse AA because I have not been able to shift the second A. Okay? So if I just do reduce here, which I am supposed to do as LR0 construction, then I'll get a wrong parser. So this tells me that's a very simple grammar, a very simple case, which tells me that there are possibilities that there could be the same state could have completed an incomplete item. And that could lead to what is classically known as shift-reduce conflict. So here we have a shift-reduce conflict which needs to be somehow broken. And LR0 construction for this grammar fails. I cannot have an LR0 parser. But that's the basic thing. Okay, so this was LR0. So we have not yet answered as to what is the solution for not being able to resolve the shift-reduce conflict. I'll come to the solution. Before that, I just want to walk you through bigger examples. So this is the example grammar that we showed here, grammar 6, and this is the state machine for grammar 6 and the parts table. So I'm not, again, I will not walk through the steps of the state machine. It's like it starts at this state here. Here they are not calling it state 0, they are calling it state 1. This example I have not drawn. So you can see it's taken from a presentation in SlideShare. So I did not take the pain of renumbering the states, but you can pretty well understand that this is the starting state of the whole parser. So the dot starts at the beginning, does a closure for these two, and then it has a transition on X, a transition on L, on opening parenthesis, I'm sorry, on X, on opening parenthesis, and a transition on S. A transition on S brings it to the accept state, which is state 4. And this gets you a completed item, which is in state 2. So you can see in state 2, you have a completed item, S produces X, rule number 1. So that is all reduced state. Whereas if you have an opening parenthesis, then you have opening parenthesis dot L. So you have a whole lot of closure coming from the L. Again, on opening parenthesis, you come back here, which is what you expect, because you will keep on accumulating. S gives you this, that L gives you S, and then S again gives you this. So you keep on accumulating opening parenthesis. And but you can also get a X. You go back, go to state 2. You can get an opening parenthesis. You are here. You get a S. You will come to L produces dot S, which is state 6, which is again is a single item. So single complete item. So this is the reduction state for rule number 3. Then you have transition on L, which takes you here to state 5, wherein so you have L here, so it takes to opening parenthesis L dot closure, and L produces L dot comma S. So these two items, state 5. And from this, you can get a closing parenthesis, go to state 7, which is a complete item, again, reduction by rule number 2. Or on this, you could have a transition on comma, which takes you here, state 8, where you again have closure, and again have transition on X and transition on opening parenthesis. And then you can have a transition on S, which takes you to state 9, which is reduction by rule number 4. So you can see that here, in every case, in state 2, state 6, state 7, state 9, in all of them, you have a single complete item, which makes this a LR0. I mean, this is I just included this to show you that it's not only necessarily that is a pathological examples only will give LR0 parsers. There are LR0 grammars which are more endowed, like this one, and you can actually have an LR0 parser. You don't really need to look into the input for deciding if you have to reduce. This will always work. Okay, so this is a workout which again you should not see. This is for a string I have worked out. You should not look at that. You should try to work it out yourself. There are practice examples given. Okay, so now let us get back here to that original question. What happened? We had a conflict. What happened? Shift reduce conflict. Back to that grammar. We had a conflict. So again, in state 2, by S producing dot A, this item, we say that we should shift the A and remain in state 2. And the last item, S producing, the complete item S producing A dot, say that we have found a handle we should reduce by production 2. We have a shift reduce concept. Now we try to look at something different. Let's look at what is the follow of S? You remember, follow is a set of terminal or symbols or dollar that can occur immediately to the right of S, the right of a non-terminal in any sentential form. So we are questioning that what is the follow of S? What is the follow of S? Naturally, S is a start symbol, so follow of S is dollar. And there's nothing after S here, so follow of S is only dollar. So we are saying that whenever we reduce, then at that time, if I'm getting S after reduction, then at that time, the symbol to the right of it has to be a dollar. It cannot be anything else. Whenever I'm reducing, I will get to a configuration where I have S in the sentential form, like in here, like in here. And in that, the symbol immediately to the right of S has to be a dollar. Now, what happens when I reduce? If I'm reducing the A to S, there is some input existing. That input could be A or it could be dollar. Now, if that input is A, then after reduction, I would have got an A after this S, which is not possible according to the follow. Follow does not say that I can ever have an A after S in a sentential form. So I can say that if my input is A, then I cannot have a reduction, because if I reduce when my input is A, look, I'm looking ahead. I'm looking ahead. I'm not deciding based on the state anymore. I'm looking ahead. Say if the input is A, then this reduction is not possible, because this reduction will get me to a sentential form where an A will occur to the right of S, which violates the follow observation. But if my input is dollar, as in here, as in here, as in here, then I will take the reduction, because that is what is valid. So now you can see that the same state which had complete and incomplete item have their actions divided based on the input. So here the shift reduce will be resolved in favor of shift. I'll have 2A S2, whereas on dollar I will have R2. It's not only the state now that decides that I have a reduction, but it's the state and the input which decide whether I reduce or I shift. So I cannot have an LR0 parser for this grammar, but I can have a parser with a simple look ahead to resolve this. Let me take another example. Here is I have not separately, oh yeah, the grammar is here. So this is the plus written in right recursive form. Purposefully written in right recursive form. Just, do not worry about the semantic consequences of it. Just take it as a grammar. So you construct this table. I'm just taking another example to show you, what I mean. I have a dot at the beginning. So we have all these closures. This is the starting state. Then I have a transition on E, which brings me here, which is the accept state. I have a transition on T, which brings me here, T dot plus and T dot. I have a transition on X, which brings me to a complete item state 5, which reduces by rule number 3. I have a transition on plus, which takes me here along with the closure, on which I can have transition on X, on which I can have transition on E, which takes me to state 6, which is reduction by 1. I have a transition on T here, which takes me back to state 3. So I have state 5, I have state 6, I have state 2, which takes care of the 3 reductions. Now I have an issue with the reduction with reproducing T. Look at the state 3. I have a complete item, I have an incomplete item. In the complete item, I'm saying that I have completed. So state 3 must reduce. So it should just do R2. But on plus, it is saying that on plus, it should actually shift. So again, in this question mark entry, 3 plus, I have a shift reduce conflict. So this says that this item E produces T dot plus E, that we should shift on plus and move to state 4. Here, like this. or by the complete item essay, it should reduce by production rule 2. Again, we will make use of the follow. So what does it tell me? What can follow T? What can follow E? Because if I reduce by this E, then what can follow? So what can follow E? If you compute it here, naturally it can be dollar, right? It can be dollar because you have the dollar here. Can it be plus? It cannot be plus, right? So I can say that in state 3, I can reduce only if I have dollar. But I cannot reduce if I have a plus, because that will mean that in the sentential form, I'll have E plus, which is not possible according to the follow of E. Follow of E is just dollar. So I will reduce this 3 plus as S4 shift and do the reduction only in dollar. So again, I'm using follow to decide whether to shift or to reduce. So back to this. So the class of parsers which use the follow information to resolve between shift reduce conflict in an LR0 parser and are able to do that are known as SLR1 parser. S stands for simple. It's a simple LR. And then 1 stands for the fact that now we are doing one symbol look ahead. So what is an SLR1 parser? It's the same LR0 items, collection of LR0 items as we did. The closure is exactly as we did LR0. The state is a collection of LR0 items. All those are same. Shift, reduce, those actions are same, except that on reduction, by a production number, only on the input symbol that belong to the follow of the left-hand side. This is not what we had considered in LR0. In LR0, we just did it by the state. Complete item, just reduce. Here, no. You reduce only when the input is in the follow of the left-hand side non-terminal to which you are reducing. So you are at this point in this part are using one symbol look ahead for the parser. So that is precisely what we are doing here. So you reduce by a production S, generating something on all symbols K that belongs to T if K is in the follow of S. If it is not in the follow of S, then you do not accept that. Then you do not do a reduction on it. You will have to either leave it blank if it cannot happen, or if there's a case of shift, you'll shift. For example, here when you apply this, by LR0 for state 3, this whole row would have been R2, R2, R2. By using the follow, we are saying that follow of E is only dollar. So you have R2. We have in state 3 a transition in plus. So on plus, we have S4. And there is no possibility of doing anything on X, because neither dot precedes X in any item in this state. So there is no shift possibility, and neither X belongs to the follow of E. So there is no reduce possibility. So if in state 3 X is indeed in the input, then it's a blank entry, which means it's a reject error entry. So you can very easily understand that by LR0 canonical construction of items and state transitions, it's pretty easy to construct an LR0 parser. And if that LR0 parser has shift reduce conflict, then it is easy to use the follow information to construct an SLR1 parser. So naturally, any grammar which has an LR0 parser does necessarily have an SLR1 parser, but not the vice versa. The grammar that we have been using, the basic expression grammar with two operators and ID. The parenthesis expression is not used in this case. Is a practice example for you for SLR1 parser. This has SLR1 parser. It looks something like this, but I will again suggest that you just work it out. Let me stop here and see if there are questions. Yes, please. If there are questions, please let me know.
There is one question in the chat.
In G4 example, when in state 4 on getting symbol A, B, or C. Okay, no, this is your coded name, DVIJ. Okay, DVIJ. Let me get back to that point. I think. Am I on the right slide, DVIJ?
G4, he said.
Yes, sir. Sir, I think now I understand it.
Right. Now you would understand it, because it is. It is possible, of course, that LR0 parser may miss some of the error conditions, but that really doesn't matter. But the whole process is, can you construct a parser which will work really for the correct string? And this is I mean, as you'll understand, is LR0 is hardly what we will do. I mean, no parser generator will give you an option to do an LR0 parser, because the grammar set, LR0 grammar set is really small, not rich at all. We'll typically do LR1, or I mean, we would actually not even do SLR1. We'll typically do LR1 or LLR1. Any other question? No. Okay. So let me just spend the next couple of minutes raising some of the closing issues, because not much time to really complete the LR1 stuff. Okay. So we saw the LR0 parser, and we saw if LR0 has shift reduce conflict, then we can resolve it by using the follow information of the left hand side. Okay, so now the spanner in that design. So consider a grammar here. S produces L and R you can kind of take as left hand side and right hand side to make a mental map of what you want to do. Left hand side, right hand side, or S produces R, just the right hand side. L produces star R, right? So you can see that it's kind of a pointer assignment, which is for which the grammar is being met. Or L produces ID. So what can be the left hand side? Star of some right hand side, where it's a pointer expression. And you have a right hand side. And what can be the right hand side? Anything that can be the left hand side. So this is the grammar. And I'm not again going through. These are the states. These are the LR0 states as you construct them. Great. Now, where is that you have a problem? You have a problem in state 2. This is your problem state. This is the first item in state 2 tells you to shift, and the second tells you to reduce. So you have a shift reduce conflict. And now, having known a little bit more, we can say that we have a shift reduce conflict on equal to symbol. the assignment symbol. Yeah, because others are no shifts possible. So at best there could be error. So let's see what is. So what do I need to know? That can I reduce on what are the symbols on which I can reduce depends on the follow of the left hand side symbol R. So what is follow of R? Now you can compute the whole of follows. Here I'm just showing by a construction. If I say S produces L assignment R, the first production. L produces star R. L produces star R. So here I have a sentential form star R, assignment R, where assignment is right after R. So I will say that the assignment is in the follow of R. Now you have a problem, because in SLR you are deciding based on the follow. And so far the SLR example we saw there, the symbol in the follow and the symbol on which we had shift in the same state were disjoint. But here you can see we have a shift on assignment, and assignment also belongs to the follow of R. So using follow, we cannot still resolve shift reduce conflict. So this is a case where not only LR0 has a shift reduce conflict, but SLR1 also will have a shift reduce conflict. The question is, can you actually resolve it? The answer is yes. And the answer lies in the fact that if you look into this, this derivation of how did I come to follow, you'll find that I've come to follow using this, replacing this L by star R by using this production. But here the question is about R producing L. Now, if you try, you have to really try with this grammar. If you try, you'll find that if you are in the situation where you are doing R producing L, at that context, you will not be able to get that equal to symbol. In other words, what you're saying is follow looks at immediately to the right, but it does not look at the left context of how did you get to that sentential form. So if we could somehow remember that left context in a better way, then we could decide what action should we take on this input equal to symbol when we have seen a string which is reducible to L. And the class of parsers where we do such things are known as LR1 parser. So I'll just, I have just a couple of minutes, so I'll just live with the basic definition, and then we'll come back and do it on Saturday again. So consider a grammar, a different grammar now, because I'm taking a grammar which is truly LR1. Augment it. Now, in terms of item, we extend the LR0 item. We say that an LR1 item is like the LR0 item, but it also has a terminal symbol coupled with it. It's kind of a doublet. So it's an LR0 item and a terminal symbol, which is called the look ahead symbol. So what we say is at any point when the dot is here, alpha dot beta, in LR0 we are saying, what do I expect to see? I expect to see whatever can happen from beta. Now I'm saying that I'm keeping track that it's not only whatever can happen from beta, but I expect to see whatever can happen from beta A. After whatever has happened from beta, the A will be there. As a dot moves to the right hand side of the production, its token remains attached to it. So Now it's say, what is the fun? Beta will produce something. How would you see A? Yes, in general, I would not. In general, I would not see A. But what will happen? I keep on moving the dot through this process, and eventually beta will become epsilon when the item gets complete. In LR0 construction, at that time, I did not have any information of what I expect to see. That information is gone because its item is complete. I only say I'm in the state I reduce. But here, having maintained that look ahead symbol, having maintained that I expect to see not whatever comes from beta, but whatever comes from beta E. So when eventually this beta has disappeared as an empty string, I know that I expect to see it. That is a specific look ahead that is possible. So it'll take time to settle down, but that's the basic concept. So these are the examples. Like these are different LR1 items. Second is what is the closure? So if I have an item like this, A produces alpha dot B beta T. If it is a production, if it's an item, LR1 item, then what is the closure for that? Naturally, I will need to take a LR0 closure. That is, if B produces gamma, then I have to include B goes to dot gamma. That is the LR0 part of it, which is what we have done. Now, what will be the look ahead for this item? The look ahead for this item, just see that B is producing gamma. Right? So what do you expect after that B? Look ahead is what happens after that. What is that can happen after this B? Is beta T. Because here you are saying that I have seen up to alpha. Now I will see B, whatever comes from B. Then I'll see beta, whatever happens from that. Then I'll see T. This is what you're saying. Now your B is producing a gamma. So after B has produced gamma, after having seen that gamma, what do you expect to see is what is in the beta T. So what will beta T give you? T is T. Beta is a string of terminal, non-terminal. So it can give you different terminal symbols. It can give you epsilon. So what I get to see is beta T is nothing but first of beta T. So in terms of taking closure, all that I need to do is to do a LR0 closure, which is introduce all productions with a dot at the beginning of this non-terminal. And for each one of them, put a look ahead symbol, which is what comes from beta T, which is what comes from first of beta T. So you have, so one item may have multiple different look ahead symbols coming in now. So rest of it is the same. The closure is completed transitively. So you have this S produces C dot C dollar. So S produces C dot C dollar. Now C produces these two. So you will have these two. Now here your beta is empty. Beta is empty string and T is dollar. So your look ahead just remains dollar. Consider this closure. C produces C dot C, C or D, which is now you have this item will happen at some stage as an LR1 item. So you have two items here actually, which is C goes to C dot C, look ahead is C, C goes to C dot C, look ahead is D, just compactly written together. Now this will include other productions from C, both these productions. And as you can see there, look ahead also will be C or D. And then the collections of such LR1 items will give me a LR1 state. I think at this point I should stop. I will continue in the next class. If there are some questions, let me take that. So what we have seen is we have seen that based on the construction of items, we can construct LR0 items, their canonical, their closure and canonical collection, and based on that, completed items being single items in state, we can do a very easily do a shift reduce parser based on the state. Then we have seen that there could be shift reduce conflict because the same LR0 state could have shift as well as reduce possibility. And then we saw that we can resolve that possibly by using the follow information of the left-hand side non-terminal of the production that we are about to use in the reduction. And that gives us to the SLR1 parcel. Then we saw again that there are grammars for which SLR1 is not possible. So now we are trying to look at an LR1 where along with the item, we are trying to compute that if I'm at this item, then what could be my possible look ahead? And I've just outlined that process. We will continue in the next class. Is there any question that may?
There's a query regarding the test syllabus.
Test, which test syllabus? For the quiz?
Oh, yeah, must be quiz.
For the quiz, it is from the beginning till whatever we have done. What is that? I mean, I thought this is a third year class, right? So people know how the syllabus goes. It's up to what you have done. So obviously LR1 is not included. But still, since you are asking this question, I'll request Srijani. Srijani, please send out a mail explicitly stating what the syllabus. Okay.
Yes, okay, sir.
So you can just refer to the. So if you are leaving out some part from today's discussion, then you can just let the students know. Okay.
Yeah, okay,
Yes.
sir.
Just send out a mail up to. I mean, you are uploading the module presentation, so just mention up to which you have covered.
Okay, sir. Yes.
Any other question? No? Okay, good. So just two things. One is please keep a note. We will again send out a mail to remind that this Saturday there will be no tutorial because this Saturday we will have a lecture class from 2, wherein I will complete this small remaining part on LR1. But most importantly, we have to actually talk about the Bison generator. So there will be a major discussion on the Bison generator. So please make sure that you do not miss the discussion on Saturday, because in the 1.5 hours, I'll probably spend the initial half hour closing on the LR1 construction. But finally, end of the day, we are not going to do this construction by hand. All that we are trying to understand are configurations where the shift reduce conflict can happen, and what are the possible ways this might be resolved. So that is one thing I wanted to remind you on. So while coming to the meeting, don't go to your respective tutorial groups. Come to the theory class group. That's one. And second is, as you all are aware, we will have the quiz, theory quiz, as well as laboratory quiz. And there will be, like we did in the trial quiz, there will be separate Moodle login for that, which will be given a while before the quiz. There will be a mail sent out. Shuman will send out a mail telling you explicitly when does your theory quiz start, and we'll have a buffer time. It's a 1 hour quiz, but we will keep a 1 hour 15-minute window for you in case you have issues, because this is a live one. So anything that you cannot do, you cannot do. The timer issue, Ishan, you are reminding, we have told them. I hope that will get resolved. They have assured that will get resolved. Now, we have no way of checking it out till we actually go live. But even if there's a timer issue, that will be some issue of impatience. But it's same for everyone. So it really does not make much.
But all of us are having some form of watch with us anyway, so that we know.
We'll have to follow that, because we did some tests with the viewability of the timer. It's probably an issue with the your OS and the browser. I mean, the best way to fix is to use the latest browsers, particularly latest Chrome. But then I understand that all of you may not have systems where that may be possible. So do not worry much about that. Do keep your stopwatch on your mobile handy so that you do not have that. So we will have first the theory quiz for 1 hour, for which we'll try to slot 1 hour 15 minutes, and then we will have a health break for 15 minutes, and then we'll again have the lab quiz for 1 hour, for which also we will have 1 hour 15 minute given. Now the target time of when the theory quiz start, when the lab quiz will start, all of that will be sent out in a mail by Showman earlier, and also the basic outline of what I think the lab quiz is simple. Lab quiz is on Flex. So anything and everything on Flex. The theory quiz, Srijani will send out as you're asking what is the syllabus, and the links to actually log in for the Moodle will be sent out about an hour before, or half an hour before the actual beginning of the test. Showman, am I missing anything in announcing to the students?
No, sir, it seems fine.
Seems fine. Okay. So that is it. I mean, just in case, like we did in the trial, just in case there is an issue, during the theory quiz, we will, some of us will remain logged on to the theory class. Showman, please, can you make that happen so that we can log on to the theory class during that time? And similarly, during the laboratory quiz, some of us will remain logged on to the laboratory class as well. So in case you have some showstopper, not much that can probably practically be done, but in case we can help in some way, or at least know what issues you are having, will be available on the login. Okay.
Okay, sir.
Professor ISG, anything else? Otherwise, we'll
It's fine. Absolutely fine.
Okay. Thank you then. Thank you all very much. Have all the best for your pair of quiz. I hope it goes well system-wise as well as your performance. Take care.